In this video, we'll look at section 10.3 regression, and our objective is to use the TI calculator to make a scatter plot, find the line of best fit or regression line for a set of bivariate data, and use the line of best fit to make predictions. Notation for equation of a regression line. In algebra, we use the y equals mx plus b, where m is the slope and b is the y-intercept. For the y-intercept of a regression equation, the population parameter is b subscript 0 and sample statistic is b subscript 0. This right here is a beta and then a b. The slope of the regression equation is beta subscript 1. For sample, it's b1. So our equations for regression lines will be in the form y hat, that represents a sample, is equal to b sub 0, the y-intercept, plus b sub 1, the slope, times x. So requirements to find a linear regression: the sample of paired data must be a random sample of quantitative data. When we look at the scatter plot, it shows the points approximate a straight line pattern. And then number 3, outliers that have a really strong effect on regression equations. So we remove any outliers if they are known to be errors. And then we consider the effects of outliers that are not known errors. So sometimes in statistics we'll find the regression equation with the outlier, without the outlier, and then really take a look at the outlier and see if it's an unusual error of some sort or just an unusual result. So for our first example, we have, this is problem 14 from the textbook. We have a data list of PSAT and SAT scores. It said one subject not included in the given table had a PSAT score of 229. Find the best predicted SAT score for this student. Is the result close to the reported value of 2,400? And then given that the data are from volunteered responses, are the results valid? Well, our requirements right away, you can tell that this is from a volunteer response. So our results probably are not going to be valid, they would be questionable, but we're going to go ahead and analyze the data anyway. So to check the other requirements, which are see if they are in a linear pattern and see if we have any outliers. I've got the data typed in already into my list 1 and list 2. So to make a scatter plot, let's see, I'm going to get out of here, second quit. I'm going to check y equals. I don't have anything in there. So I'll go to my stat plot, turn it on. I've got my x's in list 1, y's in list 2. So this is set up, got scatter plot chosen. So I hit zoom option number 9, and you can just type a 9. Ooh, there's my scatter plot. That looks kind of funky. I see something way over here that might affect the line. So I'll have to pay pretty close attention to the R, the correlation coefficient. Okay, but I'm going to go ahead anyway. It looks like there's a positive correlation or a positive linear correlation in between. That's pretty far outside. That may or may not be. We'll see how it goes. All right, so to actually find a line of best fit using the calculator, let me scroll down a little bit. We're going to go, let me clear out of here. We're going to go to Stat, over to Tests, the same as we did in 10.2. Scroll down to Linear Regression T-Test. Enter. I've got my X list in list 1, Y list in list 2, frequencies 1, select not equal to 0, regression equation. What you can do right here is you can select where you want your calculator to store the regression equation. I think it would be really neat to have it in Y1 so I can graph the line and the scatter plot at the same time. So here's how you do that. You don't have to do that, but here's how you do it. So regression equation, to get Y1, you press variables key, arrow over to Y variables, function, and then Y1, and it will print Y1. And when we calculate it, it'll actually store your equation in Y1. Okay, so we hit enter to calculate. So here's our regression line, is of the form y is equal to a plus bx. A from the calculator is the y-intercept and b is the slope. So as you scroll down here, Let me go down a little further here. A is equal to 1313.719. So if we round that to 3 places, that's our A, and that's the y-intercept of our equation. B is equal to 4.562. So B 4.562, that's the slope rounded to 3 decimal places. So our line of best fit, or our regression line, is y hat is equal to 1313.719 plus 4.562x. So it's written backwards from how you usually write these in algebra. Okay, where x is equal to the PSAT score and y is equal to the SAT score. So let's scroll down a little bit just to see what the R value is. Not very good, right? 0.54. So if we go back up here and look at the p-value of 0.16, honestly, that tells us that a line is not a very good fit for this data. Okay, we'll go ahead and use our line, but it's not a very good fit. All right, so how to make a prediction using a line of best fit. The student in the problem above had a score of 229 on the PSAT score. We substitute that value for x in our regression equation, and we end up with a value of 2358.417, and that's the predicted score on the SAT test. The predicted value is close to the actual score of 2400, but the prediction is actually lower. Okay, and the question about is this a valid? The responses are from volunteers, so the results aren't really valid. So there's two things not going very well for us here. The first one is the R value told us that this isn't a very good fit, along with the P value. The other item that worked against us a little bit there is we saw an outlier. Third thing that works against us, it's a volunteer sample. Okay, but I do want to show you that when you click y equals, it actually wrote the regression equation in here. It just rounded it to a lot more spaces than we would have. So if you want to graph that, let's see what happens. There's our regression equation graphed along with all of our scatter points on the scatter plot. So you can take a look just how well your line fits the data. And again, in this case, it's not great, but at least it goes through the steps on the calculator of how to do it. And you can answer the questions on the homework. But it also a good example too, because it allows us to take a look at some of the cautions. Look at how far away some of these actual values are from the line. Okay, maybe if we took that value out right there, we'd have a better fit, and that would be something to explore.